So thank you very much to all for attending. As Amelie kindly introduced me, I am Teresa Cebriano. I'm working at CLPU. I am a material scientist mainly, and I'm working here almost for 3 years ago. Now I'm going to give some ideas about our radiation sources based on laser plasma interaction and their applications in material science under the frame mainly of the project REMADARI. So the CLPU is a Spanish unique scientific and technical infrastructure. It is located in Castilla y León region, specifically in Salamanca. Our organization is formed by 3 bodies, which are the Ministry of Innovation, Science and Universities, the Castilla y León Regional Government, and the University of Salamanca, which is one of the oldest universities in Spain. The center hosts the Laser VEGA. This name in this way due to the star and the coincidence that Vega is the patron saint of the city of Salamanca. We have 3 main lasers line called VEGA-1, VEGA-2, and VEGA-3 with 200 terawatts and 1 petawatt respectively, as you will see later. This is our network. We are partners in Laserlab-Europe, LIBS, and in Eupraxia project. As a facility, we have these statistics for the access. Our average is 3 calls for access so far. And we have gathered at least 42 institutions from different countries covering topics such as particle acceleration and radiation, nuclear and plasma physics, laser technology, astrophysics, and material science, among others. This is the schematics of the 3 lines, VEGA-1, VEGA-2, and VEGA-3. Nowadays, we operate mainly in VEGA-2 and VEGA-3, which are our 200 terawatt and the petawatt line. Both can be compressed up to 30 femtoseconds. Our central wavelength of these pulses is 800 nanometers, and we can operate at a repetition rate from, in the case of VEGA-3, to 1 Earth, and in the case of VEGA-2, in 10 Earth, in single shot or burst mode. We have a high constant ratio, greater than 10 to the 10, and high flexibility to perform pump and probe experiments. Now, this is our present target area. We have the possibility of these configurations. VEGA-2 can operate at short and long focal length, reaching from 10 to the 18 to 10 to the 20 watts per square centimeter, and at a repetition rate of 10 Earth, as I said before. The case of VEGA-3, we have for the moment the long focal configurations, which provides 10 to the 20 watts per square centimeter and the capability of performing the double pulse configuration. Now, I'm going to pass to describe briefly the diagnostic techniques we use to characterize the generated particle beams. We have calibrated active and passive detectors, such as scintillators, radiochromic films, and image plate detectors. These elements allows us to estimate the charge by imaging or other scanning processes. We have also a Thomson parabola spectrometer to characterize the different particle species and fluencies. We have also this charge particle spectrometer coupled to a microchannel plate for charge particle detection after the deflection by this magnetic dipole. We have also time of flight detectors that are able to retrieve the particle energy. We are also working on particle and X-ray radiation based on commercial cameras. Our intention is to calibrate these devices in order to quantify the currents of different particles. But for the moment, we are studying the resolution in X-ray images and the response two electrons and protons with setting up similar than this one. Notice that we remove the borosilicate glass to avoid an energy filtering in the acquisition. For more information, this is the person in charge of this device. Also, we are developing the calibrations of these spectrometers for the XUV, near infrared, visible, and X-ray ranges. So these are the main ways that we characterize our particle sources. Now I'm going to switch to the particle sources we have and their characteristics. As I mentioned before, we can operate either in VEGA-2 or VEGA-3 lines, depending on the required characteristics of the particle bands we want. This is the case of VEGA-2, with the two possible configurations with long or short focal length. In the case of long focal length configuration, we used to use gas targets to accelerate mainly electrons. These electrons are accelerated by a typical mechanism called wake field acceleration. In this regime, the laser field sweeps the electrons in the plasma, creating a wake of relativistic electrons of energies up to 500 mega electron volts. These electrons, at the same time, are trapped into potential well following the laser and oscillating almost at the speeds close to C. These fast oscillations originate betatron radiation, as you can see here, with a critical energy of 10 kiloelectron volts. So in summary, this regime can generate short and brilliant sources of electrons of the order of picocoulomb per mega electron volt. These electron pulses have durations at source of few femtoseconds, and they have low transversal emittances. Regarding the X-ray betatron source, due to the small area, which is of the order of microns, in which the electron oscillations take place, we can consider these sources spatially coherent. This is an example in VEGA-2, which is related to other particle acceleration strategy. This is called target normal sheet acceleration. We use this regime in case that we want to accelerate protons and ions. The mechanism is with a thin foil, more or less from 5 to 10 micron. It's irradiated by VEGA-2 in this case, and the laser prepulse create a preplasma on this target front side, and the main pulse interacts with this plasma, accelerating mega electron volt electrons, mainly in the forward direction in a sheet-like shape. These electrons drag the positive charged ions and the protons like in a capacitor, reaching mega electron volt energies. The result is this exponential proton distribution, in this case with a cutoff energy, which is depending on the electron driver. In this case, the cutoff energy is 9 MeV. We can reach higher energies, in this case with VEGA-3. This is a spectrum of the Thomson parabola in which our maximum proton energy is 20 mega electron volts. So that in summary, I add this table of pros and cons of these sources. We can suppose as pros the high brilliance nature of these sources, also the ultra-fast character they have, and the compactness in comparison with other current accelerators. But the divergence, the energy spread, and the multi-species nature can represent a disadvantage if the application, for example, requires monoenergetic or collimated bunches. I don't know if I mentioned that in TNSA regime, we will have another sources such another positive ions or the electrons and also X-rays. In addition, these sources have the property of low emittance, so this indicates that can be manipulated, for example, by magnetic elements. These magnetic elements can be energy selectors, quadrupoles, permanent magnet quadrupoles in this case, solenoids, etc. But these examples have been designed and built here at CLPU. This is the example of the proton focalization with the permanent magnet quadrupoles, in which we have characterized the charges by scintillators located on this wheel of detectors. We have characterized the energy by high-pass filters, mainly of aluminum foils attached to the scintillators, as you can see in this table. These results of focalization are in agreement also with the deflected energies induced by a kick or a quadrupole transversal movement. In this case, we move the second one. As you can see, we reach spot sizes ranging the centimeter size in RMS. In this experiment, we also explore a possible application related to lithography or proton writing. This is the setup. We place this mask in between the third quadrupole and the detector wheel. And in this way, we could reduce the spot sizes at the focal plane. As you can see here, the RMS is ranging 1 millimeter from 1 centimeter that was before. Also, the pinhole of the mask can act as an energy selector due to the focusing process. In this example, you can see that the first hole is aligned with the spot. So this can clean the signal in terms of overfocused particles that have different energies in comparison to the central one. This result would also have some relevance in ion implantation or scanning processes or in the field of the X-ray spectrometry, as it is the next example. This is one of the most developed techniques. The detection of the characteristic X-rays can provide us a quantitative idea about the composition of the samples by elementary analysis. In this way, we can generate characteristics X-ray by electrons, protons, or ions. The energy dispersive X-ray emission is a widespread technique that used to be carried out in a scanning or transmission electron microscope. In the case of the particle-induced X-ray emission of pixel, the incident beam is based on protons or ions. In the case of protons, the energy deliverance in matter is located in one plane at a certain depth, depending on the proton or ion initial energy. So this makes this technique interesting, for example, for an stratigraphic analysis, and in addition, this technique can be performed in air. Both techniques are considered non-destructive, and here I have two experimental setups at CLPU as an examples. The example A is the EDX, and the example B is the pixel. In the first one, VEGA-2 arrives to the target, creates the plasma in the TNSA regime, accelerate the electrons and the protons and the ions. This aluminum foil is just here to avoid the debris deposition. And the second one, which is the pixel, differs from this dipole that is removing the electrons from the ions path. The results are here in these two spectra, in which you can see the detection of the K alpha and beta lines relative to chromium and copper. And this is the amount of each element we have as a function of the depth. This is regarding the protons and the mixed beam. we are speaking about the electrons in the frame of the wake field acceleration. The relativistic electrons pass through this filter, and their static potential interacts with the crystal lattice, emitting X-ray photons as a function of this orientation. Then these photons are diffracted by the lattice, resulting in this sharp emission. This is called parametric X-ray radiation. This peak can be slightly tuned by tiny rotations in which you can see the shift frequency so that the energy emission can be tuned. Here, there is an example of the Betatron radiation that I explained before due to the oscillations of the electrons in the weak field acceleration. So this Betatron source can be considered spatially coherent due to the small size, and it's suitable to make phase contrast images, as you can see here, which this is an example of an image of one seed. These photon sources can be applied as photon sources themselves, high energy physics or radiation hardness, but also in flash radiation therapy. The next example is related to the growth and the synthesis of different micro and nanostructures. In this case, we focus VEGA-3 on a thick target, about 1 millimeter, to evaporate and ablate as much material quantity we can, and we place all this silicon substrate in the chamber, as you can see here. We have these 3 examples of liquid, solid, deposition, but also the presence of tiny nanoparticles in the air as a consequence of the laser spot profile intensity distribution. We have also a scanning electron microscope as a complementary technique. This is a phase EVO HD25, in which we can perform EDS, as you can see here, the elementary analysis, but also the electron backscatter diffraction, as you can see in this Kikuchi pattern. For sure, we can perform the electron secondary images. Also, we have a lab which is dedicated to the microprocessing and other applications with all of these laser systems. We used to use this at the right, these setting ups. And in this lab, we can perform laser-induced periodic surface structures, microprocessing in metals, target processing as well, secondary electron filters, as this for plasma studies, as this example, but also laser-induced damage threshold or LID. Another application do here is the laser-induced breakdown spectroscopy, in which this femtosecond laser irradiation creates this local plasma. This plasma has a characteristic visible luminescence that gives us an idea about the elementary composition of the sample surface, just in a parallel way than the X-ray peaks and EDS. This technique does not need a sample preparation, and a small portion of the sample is required. Has also the capability of perform mapping of surfaces, as you can see in these images that are teeth from different ages. These are present teeth, these are medieval teeth, in which the strontium-calcium ratio is represented. This ratio gives an idea about the eating habits and location, but unfortunately in this example do not reveal any change in this ratio. In addition, we are working in medical and chemical application, like soft and hard tissues cutting, catalysis in chemical reactions, or the measurements of the glucose concentration in the blood. We have working also in laser filamentation applications. And last, We are under an upgrade process in which we are building our second target area here. Our first intention is to introduce VEGA-3 in short focal length configurations, which will duplicate the number of staff, the number of experiments, and also the number of results. So thank you very much for your attention. This is my email. All of you are invited to ask us before applying the access in remade or whatever you want. And thank you a lot for your attention.